In this lecture, I'm going to introduce some generalities about real-time operating systems. And let's first look into what real-time means. A real-time system possesses explicit temporal constraints. It does not mean that it has to respond fast. It means that it has to respond before a given deadline. There is a notion of soft real-time versus hard real-time. For soft real-time, the process result is still valid after the deadline, while hard real-time means that the process result is not valid after the deadline. In addition to that, you will have to consider the notion of criticality of a system. And a system is called critical if any malfunction leads to significant consequences on the environment, the people, or the system itself. The example I gave all the time in this class is the notion of an airbag system. Well, if your airbags deploy after your head crashed into the steering wheel, you can consider that you missed a hard real-time deadline and that system was critical. How to understand better how to deal with real-time systems, I would like to discuss again our various firmware strategies. And I would like to go through that again. So you remember the polling strategy for implementing an embedded system, where you have this giant loop where you will just do some basic tests. Does A requires processing? If it requires, go for it. And test for B and so on and so forth. You will remember that polling, while effective for simple processes, is creating a problem if one of the specific process is taking a long time. The entire system will lose reactivity. So in order to avoid that, we introduce the interrupt-driven programming, in which every single process is dealt with on demand using interrupt service routines. I receive a message on the UART, let me pick it up and do what the UART needs me to do. For every time interval, let's have the timer kick in and do some of the tasks I have to do, and everything can be handled in the interrupt service routine, which is good, and you have some possibilities to grant priorities between your systems, between your tasks. But what if a high priority task takes a very long processing time? You will end up locked again in your interrupt system. So in order to alleviate that problem, I mentioned one of my personal favorites, which is a combination of polling and interrupt-driven. You will receive interrupt for the very time-critical and sensitive applications, raising a flag, and once you have time, you will use a polling loop to actually go through the actions that are necessary to implement. In this particular case, one, for example, can receive something on the UART again, and just buffer this information somewhere, such that once your system has some time, we will actually process the information received on the UART, assuming, of course, that this is not too critical and does not need to be done as soon as possible. This very final sentence is actually where the problem is. You have no guarantees about when you will be able to get back to this information. And that's where the use of a real-time operating system will make sense. In a real-time operating system, you do have your various processes, and they are scheduled based on the operating system task scheduler that will be able to use various scheduling policies to guarantee enough CPU time on all the tasks, as well as guaranteeing that the real-time constraints are met. This multitasking principle is the basis of an operating system, where you will have the feeling that all your tasks are actually running concurrently, while in practice they will be running one after the other on small chunk of CPU time. That is called, software multitasking, and that's what will enable you to now schedule and arrange your task in such a way that you can deal with the higher priority ones first.